Welcome to the chapter on analog electronics. In this chapter, we will cover the basic components of analog electronics: diodes, transistors, and operational amplifiers. A diode is a semiconductor device that allows current to flow in one direction only. It has two terminals, an anode and a cathode. When the anode is at a higher potential than the cathode, the diode is forward biased and allows current to flow. When the cathode is at a higher potential, the diode is reverse biased and blocks current flow. The current voltage characteristic of a diode is nonlinear and can be described by the Shockley-diode equation. The equation is I equals I sub s times the exponential of V sub d divided by nV sub t minus 1. Here, I is the diode current, I sub s is the saturation current, V sub d is the voltage across the diode, N is the ideality factor, typically between 1 and 2, and V sub t is the thermal voltage, approximately 26 millivolts at room temperature. Diodes are commonly used in rectification, which is the process of converting alternating current, or AC, to direct current, or DC. In a simple rectifier circuit, an AC voltage is applied to a diode, which only allows the positive half cycles of the AC signal to pass through, effectively converting it to a pulsating DC signal. Transistors are semiconductor devices used to amplify or switch electronic signals. There are two main types of transistors: bipolar junction transistors, or BJTs, and field effect transistors, or FETs. A bipolar junction transistor, or BJT, has three terminals: the emitter, base, and collector. It operates in three regions: active, saturation, and cutoff. The current gain, beta, of a BJT is given by the ratio of the collector current, I sub C, to the base current, I sub B. A field effect transistor, or FET, has three terminals: the source, gate, and drain. It controls the flow of current by applying a voltage to the gate terminal, which modulates the conductivity of a channel between the source and drain. Transistors are widely used in amplification circuits. For example, in an audio amplifier, a small input signal, such as from a microphone, is fed into the base of a BJT. The transistor amplifies this signal, producing a much larger output signal that can drive a speaker. Operational amplifiers, or op-amps, are integrated circuits that can perform a variety of analog signal processing tasks. They have two input terminals, inverting and non-inverting, and one output terminal. Ideal operational amplifiers have several key characteristics. They have infinite open-loop gain, denoted as A sub OL, infinite input impedance, denoted as Z sub in, and zero output impedance, denoted as Z sub out. In an inverting amplifier configuration, the output voltage Vout is given by the formula Vout equals negative the ratio of the feedback resistor RF to the input resistor Rin, multiplied by the input voltage Vin. In a non-inverting amplifier configuration, the output voltage Vout is given by the formula Vout equals 1 plus the ratio of the feedback resistor RF to the resistor connected to ground RG, multiplied by the input voltage Vin. Operational amplifiers are used in signal conditioning circuits to amplify and filter signals before they are processed by other components. For instance, in a temperature sensor circuit, the small voltage output from the sensor can be amplified by an op-amp to a level suitable for analog to digital conversion. Understanding the basic components of analog electronics, diodes, transistors, and operational amplifiers, is crucial for any electronics engineering student. These components form the building blocks of more complex circuits and systems used in a wide range of applications, from simple rectifiers to sophisticated signal processing units.